Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process from freedom fighter Bal Gangadhar Tilak, who says, our nation is like a tree of which the original trunk is Swarajya and the branches are Swadeshi and boycott. Of course, he had told this statement during before independence, and that is still valid today, and we are all drifted away from this concept of Swarajya and Swadeshi. Let us recall what we learned in the last lecture. In that lecture, we had derived an expression for chamber pressure in terms of the area ratio, that is AB by AT, and which is also dependent on the density of propellant, gamma, and also inversely it is proportional to the, it is dependent on also the chamber temperature. So, also the pressure index, and this we have derived under the steady state condition. We can also use the expression or the equation rather for finding out how does the chamber pressure changing with respect to time. Today, we will be discussing about basically the types of the propellant grain we can have. So, as we know already that about the end burning grain, the burning will be taking place from the end, and keep in mind that this will be moving along with the length of the things, like along the longitudinal directions, the burning surface will be regressing out. This is one of them. And the another is that the where the known as the radial burning grains. In this case, the burnings will be taking place along the radial direction. If you look at, this is my x direction and this is your radial direction. So, regression will be taking place only in the, and keep in mind that this portion is restricted, that means no burning is taking place here. There might be a lot of insulation material and also the certain things which will not allow the regression taking place in this region, or inhibitors. This will be inhibitors which will be there. And we have also seen that the steady state chamber pressure will be dependent on this area ratio, as I told earlier, and it will be dependent on temperature ratio and 1 by n, and we are keeping everything constant including the throat area. That means, the P c is basically function of, I can say this is constant, and A b power to the 1 over 1 minus n. So, that you should keep in, that means A b is increasing and chamber pressure is increasing, that you should keep in mind. And keep in mind, this is the basic process of burning, that is, one is radial, other is the longitudinal along with the length. This is the, as I told, this is the length in this direction. So, when you combine these things, and we will get another kind of things, and this generally when it is restricted in one direction is going, that is basically known as two-dimensional burning. And when both the radial and the longitudinal are combined together, we call three-dimensional burning surface. So, let us consider the two-dimensional, and some examples we can think about. One is the radial burning. Radial burning surface can be various kinds, and keep in mind that the end burning is having limitation, because the diameter, this is your diameter, and it is the burning area is basically limited by the diameter, and Of course, one can increase with increasing the diameter, but diameter is limited, and if the diameter of the propellant grain is higher, then naturally the rocket engines also diameter will be higher. So, the drag will be much higher. But whereas the radial burning, lot of design one can have, and some of the design we are going to discuss. One of them is tubular, which is a very common thing. I am taking a cross section over here. If I take a cross section of this, let us say, and you will get a cross section of that, and this is the, if it is a center, this is the radial direction, this is your r directions, right. This is your center, r directions. And as this it is moving in the radial direction, this is your burning surface area. If I consider this is my burning surface area, this is regressing, it is moving this direction. So, that what will happen, this area, surface area is increasing. If the surface area AB is increasing, in this case AB is increasing with time. So, that what will happen, the more amount of mass being converted into gas, and then the pressure for a particular throat area, there will be increase in pressure, as we see that AB is increasing. If AB is increasing with respect to time, PC will be increasing. If chamber pressure is increasing, then naturally the thrust will be higher, because for the same choked conditions, right. The more thrust, so that what will happen, of course, initially it will be having, but after that there will be increase in the thrust due to the increase in pressure. And once it is consumed, then again it will be coming down, and this we call it as a thrust law. Thrust versus time is known as thrust law. You can see that burning rate is increasing, therefore, we call it as a progressive burning propellant grain, right. And let us look at another case, which is the tube with a rod. This is the same thing with a tubular, but we are inserting a rod inside. This is your rod, this is your tube, and this is your rod, and these are propellant rod. And keep in mind that when it is burned, and then this will be moving in this direction outwardly, and this will be moving inwardly. This rod will be receding or reducing its diameter as the combustion taking place, and this portion is your combustion which is taking place. This is a combustion chamber or combustion port. So, therefore, in such a way this propellant grain is designed that the amount of mass generated due to the regression of the tube and the rod, in one case one is positive, as a negative, it will cancel each other. So, that the burning surface area will be remaining constant, total burning surface area will be remaining constant with time. Therefore, the chamber pressure will not be increasing, it will be remaining almost constant, and so also the thrust. So, therefore, you will get a thrust versus time, that is the thrust is remaining constant with respect to time, and this is known as a neutral burning. This is known as neutral burning grain. So, this is a thing which is required sometimes. Of course, progressive burning is required where you want to really have something in a missile applications, and where you want to chase some kind of fighter or aircraft or some other things, you may use progressive burning propellant. So, let us look at a star. In this case, what is happening, this is a basically star shapes is given, and this is your thing and your port area. So, when it will be going, keep in mind that always that burning surface regresses perpendicular to this surface and this surface, whereas this will be is reducing, and this corner will be also curving out. So, that what will happen as it goes, these corners will be reducing in such a way that this is the area is basically decreases. So, the net area as it goes, so these surfaces will be like this, and then it will also reducing. So, that this is basically with respect to time, and it will be receding. As I told that the surface area will be decreasing with respect to time. As a result, the chamber pressure also will be decreasing, leading to the decrease in the thrust with respect to time. And you will get a thrust law like this, that means the thrust will be decreasing with the respect to time, and this kind of the propellant grain is known as regressive burning grain. And let us consider another case, that is a multi-fin kind of propellant grain, and which will be looking like that. There are one is your this fin, and there is another fin, two fins are there. So, if you look at as the time progresses, this will be regressing and this surface will be regressing, it will goes on reducing and kind of things. So, that there will be increase in the very beginning, there will be increase in the surface area because the burning rate will be very high, so many surfaces are there. So, these all surfaces will be contributing a large amount of the propellant grain being converted into gas. So, that the chamber pressure will be quickly increasing, leading to the very high thrust to start with. So, but after that this is reduced and these fins will go away, and so that this will be reduced very quickly, and then of course, after that in such a way that this is being decreasing the surfaces and this is increasing. So, almost will be remaining constant and then decreases. So, this is known as a dual thruster. So, for example, this portion can be act as a initial portion as a booster, which will be giving very high thrust, and after that it can be used as a sustainer. So, it can be applied for various application. Keep in mind that the four kinds of propellant are the burning grains I have shown you, but there might be several of, but the fundamental one is progressive, other is neutral, other is regressive, and these are the three kinds you can say which are fundamentally different in nature. And by combining all these things or various kinds of the grain design can be made, that depends on the innovativeness of the designer and also the type of propellants one can have. We will see now some of them further. And just to say that, like as I told, there are various kinds of people of use, but this is again there will be a surface which will be having known as star is a neutral it will give, because what will happen, this surface, if I take this, consider this as a surface one here. So, then this surface will be curved one, and then this will be going to that surface, and then this will be curved one. So, this will be decreasing and this will be increasing. So, that will be depends on the kind of thing which will be also taking place, so that it will remain neutral, and multi perforated one. So, this will be increasing size, like this will be progressing in such a way that it will be giving a lot of surfaces. However, this is not being used for solid propellant rocket engine, rather it is being used for hybrid engines, and there is a dog bone kind of things which will be like that. So, this surface will be decreasing, this will be basically increasing, and this also gets increased to the surfaces, because this will become curved and this will be decreasing this portion and this will be increasing portion, that will be compensated. And similarly, there is a wagon wheel, and which is if you look at this portion will be increasing, whereas this will be decreasing the surfaces. So, that you will be leading to another maybe sometimes neutral depending on that. And there is a 3 conical ports which is can be designed, and a double anchors. So, this surface area will be increasing and this will be basically decreasing, and then so that you will get a surface like that. So, there are various kinds of grain configuration you can see, but most popular is your star, wagon wheel kind of things which are being used, because that is easier to manufacture, and these are little difficult to manufacture and also to maintain the uniformity throughout. So, as I told that the configuration that uses either internal radial or external longitudinal burning surface with a restricted end, as I told earlier, and is known as basically generally 2-dimensional grain is easy to design and fabricate, therefore, it is being used profusely. But however, if you want to have a higher density of the propellant or the compact combustors in case of solid rocket propellant engine, you may have to go for 3-dimensional grains that we will discuss little later on. Let us look at various grain configuration in with the limitation of 2D. One, of course, we have seen the end burning grain, which is having a limitation and of the enhancing the burning surface area. It can be enhanced by only the increasing this diameter, that is your D, but there is always limitation of enhancing it further. So, there is a radial burning grain, and there is a grain which will be simultaneously burning the radial and the that is radial burners. You can look at like this, it will be radial burning, which is having a restrictor here. These are restrictor, but these are the gas will be coming out of here, and this will act as a boosters, and whereas this will burnt out, then you can burn use as a, this will be end burning, which can be used as a end burning sustainers. So, this combine the boosters and the sustainer together will be used as a single design. So, let us look at another one, concentric radial burning, and one is of course, the high burning boosters, that is your this portion is basically high burning booster propellant. That means, the burning rate will be high, so that you will have a higher chamber pressure, and then that will act as a booster, as it will be giving the higher amount of thrust. So, later on, once this is consumed, then you can have a low burn sustainer. This is your low burn sustainers, and which will give you the decrease in pressure, so that the thrust will be lower. And let us look at another design, in which case this is also known as a pulse motor, because this will be giving the surface area very high in case of a radial one, and this is your radial boosters. And then once it is over, then what will happen, the end burning will be started doing, and then that will be known as a basically end burning sustainer. So, this is again a pulse kind of thing. That means, in the beginning you will have a very high thrust being produced during the booster phase, and then later on there will be just a sustainer. Let us look at another one, which will be having a radial, both are radials, unlike the previous one, in which there is a radial propellant grain and also the end burning propellant grains. But in this case, this radial boosters is being used, and then later on the radial sustainer. So, this is the first one, like it will be using as a booster, and this will be using as a sustainer. So, again this is the pulse motor, this is a separate burning, that means one is over and then after that only other one, unlike the C in which the simultaneous burning will be taking place. So, therefore, a lot of combination permutation one can have, that depends on the imagination and also the willingness to design new burner for certain applications. So, let us look at the various types of 3D grain configuration. We will be only discussing about 3 of them. A question might be arising in your mind, what is the 3D grain? 3D grain is basically the configuration in which both the internal, that is the radial, and external, that is the longitudinal burning tube can be combined without any restricted end, as it is being done in case of 2-dimensional grain, is basically known as the 3D grain. So, 3D grain is little difficult to design and also to fabricate, therefore, it is needs special knowledge and you cannot really predict its burning surface area very easily. So, therefore, a lot of acumen is required for designing and developing it and also using it successfully. And it is being used to have a high density loading and also the low L/D ratio and the longer burning time. All this can be achieved by the 3D grain, 3D propellant grain as compared to the 2D propellant grain. So, therefore, it is really very much important to learn about this thing. However, this requires a specialized knowledge and also experience to use it. So, we will be discussing 3 of them. One is the conus seal design, which is having a combination of cone and cylinder. So, if you look at this is basically a cylinder and this is a cone, 3D cone which will be having, that will be giving you the radial and as well as the longitudinal. I mean, if you resolve this one, so if you resolve to this one, and also this is the cone which is combined, and then of course, if you take a cross section of here, it look like a star, and all I have shown as a star, but it can be different. And keep in mind that this is a very complex surfaces which will be producing in this case, because this is a cone and then therefore, it is also very difficult to fabricate. However, people have designed and developed it. There is another design which is a fino cylinder, that means there will be lot of fins. This is basically fins and these are the cylinder and having a surface. These are the cylinder combinations, and this is quite compact as compared to the conus cylinder, but this is also quite complex to design, and also each fin has to be properly worked so that they should not crack, and then during its operation, and as a result the chamber pressure will be increasing very fast at a faster rate, leading to the explosion. And this is little more compact, the phenocell design as compared to the conocell, and also quite complex to design and develop. And the other one which is a very compact design among all these 3 is the spherical design, and which will be the burning will be in spherical in nature, 3-dimensional. But thing is that it is having limitation of the diameter, because the diameter becoming very high, and you will get the lowest L/D ratio in case of spherical design. Of course, the phenocell design will have a lower as compared to the conocylindrical design. And keep in mind that this thing you will have to look at maybe little 3-dimensional figures in the book of Sutton and others, so to have a visualization about the things. So, with this we will stop over. In the next lecture we will be discussing about and also recapitulating various types of solid propellant grain in a very compact manner, and later on we will be moving into how to calculate the regression rate for certain simple propellant grain. So, thank you very much. We will stop over.